Welcome back, friends, to another session of fluid mechanics and rate processes. So, we have been looking at similitude and modeling, and we will continue on that. We explained in the last class what does similarity mean. So, I will go through that again a little bit, and then today we are going to understand that with the help of a few examples. So, I hope by now you have got a fair idea of what is the meaning of these two words in this phrase, similitude and modeling. So, as the name suggests, similitude refers to similarity. Okay, how do you make flows similar? So, we understand that, and then how do you model using these similarities to get the desired results? Okay, so, that whole thing is very important from an engineering perspective. So, in the last class we were looking at an example that suppose you have CD as a function of RE. Okay, that means the drag coefficient on a body could be non-dimensionalized as CD. So, this is the non-dimensional drag coefficient, and we have taken the example of an airplane, and RE is the Reynolds number, which is another similarity parameter. So, we showed that drag could depend on many parameters, but suppose we took a special case that the shape of the aircraft is fixed, we are not worried about the altitude effect. So, we are flying at sea level, we are not interested in the surface roughness, we have a reasonably smooth surface. There are no free surfaces, we are not interested in the effects due to gravity and so on. Then the CD would depend only on RE. And then we tried to understand using this idea the concept of similarity. So, if we want to look at similarity, the first thing was geometric similarity. And this means that the shapes are similar, in fact shapes are identical, but the length scales are related to each other by a constant scale. So, if I had, let us say, a rectangle in the model and in the prototype, then it is rectangular shape in both of them, and the length scales for the width and for the length of the rectangle would be in the same proportion. If the geometric similarity is ensured, then we can talk about dynamic similarity. And this is if all independent pi's are identical in the context of a model and prototype, then the parameters for dynamics such as forces, like drag, etc., are also similar. So, to illustrate this example, what we can do is we can talk about a model and we can talk about a prototype. So, suppose I have an aircraft where I am doing some testing, and let us say this is the length of the model, and maybe I have a prototype which is probably larger, and this is the length of the prototype. I had speed of um here, I had a speed of up here. Okay. And dm, let us say is drag on model, and let us say dP is the drag force on prototype. And because I have assumed that CD is only a function of Reynolds number, so the first of all I have to talk about geometric similarity. So geometric similarity would imply that if my scale factor here is Lm and Lp, the ratio of those, then all the dimensions, the remaining dimensions, should also follow this scale factor. All the angles should be identical, all the shapes should be identical. So that would take care of geometric similarity. Dynamic similarity is going to be ensured, so the flows are going to be dynamically similar if Reynolds number for the model is same as the Reynolds number for the prototype, okay, which would actually imply that if I am doing my experiments in the air just like in the prototype, then Reynolds number for the model would be rho of the air that I am going to use for the model times the velocity, so u of the model, and the length of the model divided by the mu of the air, the viscosity of coefficient of viscosity of the air for the model. This should be exactly same as rho p up Lp divided by p. Now if the medium is same, so if I use the same fluid, then of course the rho and the mu are identical for the model and prototype, and automatically you would get um times Lm is up times Lp. So what this tells me is that if I had to conduct experiments, let us say for a model aircraft, suppose this was a 1/10th scale model, okay. So original aircraft is 10 meter long, and suppose I make a model which is 1 meter long. Then I know the Lm and Lp relation, and from this I can estimate that if my prototype was flying at, let us say, 40 meter per second, what should be the corresponding speed for my model to ensure that they are dynamically similar, which would occur if the Reynolds number are similar. If that happens, if I am able to ensure that the Reynolds number are identical, then I would have ensured the following. This would ensure that CD on the model is identically equal to the CD on the prototype, okay, which means that if I knew the drag, so what is CD? CD would be the drag on the model divided by half rho, because I have non-dimensionalized it, with and maybe the length square, which represents an area for the model, and this would be equal to the drag on the prototype divided by half the density of the air I use for the prototype, the velocity or the speed for the prototype squared times Lp squared. Okay. And if I make measurements by doing experiment on the model, then I will be able to measure these, the drag on the model, and because I know everything else now, I can estimate what would be the drag on my prototype. Okay. So you can see now the relationship between similitude and modeling. Okay. So to get the right kind of modeling, I must look at the right kind of similarity and the right kind of similar parameters. Let us look at some examples. So the first example that I would like to present to you is that to estimate the power requirement of an airship traveling at 10 meter per second, it is proposed to test a 1/20th scale model in water. What should be the testing speed? And the prediction rule for power. Okay. All right. So, what is being suggested is that there is a model which is going to operate in water, and there is a prototype which will operate in air. So, let us list the parameters and then it will help us in doing the analysis. So, the length, for example, the model has a length Lm which is going to be 1/20th of the prototype. So, I am simply going to write that the length of the prototype is Lp. We have not been told what is the length of the prototype. Okay. The speed, I have the u of the model which I am supposed to find out, and the u for the prototype is 10 meter per second. Rho is the density. So, the rho for model in water. So, I am going to write down the density of water, that is 10 to the third kilogram per meter cube, but the prototype operates in air. So, this is going to be 1.226 kilogram per meter cube. Let us look at the viscosity. The viscosity of water is 1.14 into 10 to the minus 3 SI units, which is Pascal times second, and the prototype operates in air. So, I am going to write down the coefficient of viscosity for the air, which is 1.78 into 10 to the minus 5 Pascal second. So, let us see what are the important parameters. What we have been told is that there is no free surface, okay, because this is completely submerged. So, in fact, when we do the experiments of the model of an airship in water, we have to make sure that it is submerged deep into the water and there is no effect of free surface. So, we keep that in mind. We also know that there is no cavitation. If there is any, we will ignore it. Okay. So, therefore, Euler number is not important, there is no free surface. So, Froude number is not important, and we will also ignore the effect of gravity. So, therefore, we will assume that only the Reynolds number is relevant. Essentially the ratio of the inertial forces and viscous forces. So we will try to match the Reynolds number for the two studies. Okay, so we match the Reynolds number. So Re for the model is same as Re for the prototype for similarity. Geometric similarity has already been ensured. So if I want to do dynamic similarity, I must ensure Reynolds number must match. So that would imply that rho for the model times the speed for the model times the length for the model divided by u for the model should be identical to rho of the prototype, u of the prototype, L of the prototype, and mu of the prototype. Okay. This, of course, the modeling takes place in water, and for the prototype the medium is air. So I have listed everything over there. So by putting in the relevant quantities, we can now estimate what is the u for the model, and that you can see would be rho p divided by rho m times Lp divided by Lm and times mu model divided by mu prototype times u for the prototype. And I can plug in now the relevant numbers, and this would be 1.226 divided by 10 to the third. Okay, density of air, this is density of water, and I already know the scale of the prototype to the model, it's a 1/20th, so that number becomes 20 here. And then the viscosity, so for the model it is 1.14 into 10 to the minus 3, and for the prototype it is 1.78 into 10 to the minus 5, and the u prototype is 10 meter per second. The airship is traveling at 10 meter per second, and that would work out to 15.7 meter per second. Okay. So therefore, to do the experiment to ensure dynamic similarity, which means to ensure the same Reynolds number, I will have to pull the model of the airship in water at a speed of 15.7 meter per second, okay, which is larger than the actual speed of the airship, which is only 10 meter per second. So that finishes the first part of the problem about the testing speed. Now for the power. As you know that power is drag times the speed. This is, so I must estimate the drag. So drag is given as CD times half rho u square and L square. So this is my dynamic pressure and this is my area. Okay. So CD is a non-dimensional quantity, drag is in Newton, so I have non-dimensionalized it with a dynamic pressure and then a quantity which is area. This could have been an area related to the cross section area, the surface area, the projected area, but I have just used a area here which is L square. So if I look at the drag on the model, that would be CD on the model times half rho model u model square L square. And if I look at drag on the prototype, then that would be CD for the prototype half rho prototype u prototype square and L prototype square. Okay. If I want to get the power, then I would have to multiply both these expressions with velocity. Okay. So if I want to get power on the model divided by power on the prototype, then that would be dm times u model dp. And you will also note, because of dynamic similarity, the CD model is equal to CDP. This is an outcome of dynamic similarity, because we have shown that Reynolds number, if it is identical, then because only the viscous and inertial effects are important, so the drag coefficients will also be identical. Mind you, the coefficients are identical but not the drags. Okay? All right. So, if I plug that these expressions over here, then this would imply, so Pm by Pp would actually imply that, so I can get rid of these, and I would get rho m um cube Lm square divided by rho prototype u prototype cube and L prototype square. Okay. If I put in the values, then I am going to find out that this P prototype by Pm would turn out to be 0.127 if I plug the values. So, the bottom line is that I would actually spend more power in towing the model. Okay. So, although it is a 1/20th scale model, but because I am towing it in water, and you will notice the speed is larger, it is 15.7 meter per second as opposed to 10 meter per second. So, P model is larger than P prototype, okay, which is a little bit surprising, but that is what it is. So, that concludes example number 1. Okay. I want to show you now another example which will illustrate similar ideas. The next example that I wish to talk about is about a pump. So, let me write down the statement that a pump capable of lifting 5 meter cube per second, so that is the volume flow rate of water against a head of 250 meter at 500 RPM. So, that is the RPM of the pump is to be designed. So, to test that, a small model is being made. So, a 1 to 9th scale model is fabricated and tested with the same fluid, which is the water, but this time, so against a head of 10 meter. Okay. So, first, at what speed should it run? By speed we mean RPM. And secondly, the volume flow rate. Okay. So, the model, the prototype is with 5 meter cube per second, and the RPM is 500 number. What are these quantities for the model? So, we will neglect viscous losses and gravity effects within the pump. So, first question that we need to answer is what are the relevant similarity parameters. Okay. So, that's the problem statement, and here I would like to first ask that what similarity parameters should I be worried about. So, let us go one by one. We are told the viscous losses inside the pump are not important. Okay. So, if viscous forces are not important, then of course Reynolds number is not important. Okay. We do not have to worry about it. So, Euler number is important. So, pressure is important. Pressure is important, and therefore Euler must be considered. The flow through the pump is unsteady, okay, because actually it has moving parts and the RPM is given as 500. So, therefore, the flow is unsteady in pump, which actually implies that Strouhal number, which relates the frequency, that also must be considered. Okay, so, this is an interesting problem where we do not have to worry about the Reynolds number, and for dynamic similarity we must ensure that these two parameters, the Euler number and the Strouhal number, they should be identical between the model and prototype. So, if you recollect, we had defined the Euler number as the ratio of inertia forces to the pressure forces. So, it was something like rho u square by p, and the Strouhal number was something like a frequency. So, it was inertia forces and the unsteady forces. So, frequency times a length scale and a speed. Okay, so, these two numbers must be matched between the model and prototype for us to get dynamic similarity. So, let us make the same kind of table that we made earlier. So, I will do it for the prototype and for the model. Okay. So, let us talk about first the flow rate Q. So, for the prototype it is Qp, which is given to me as 5 meter cube per second, and in fact for the model this is one thing that I need to find out. Then I need to worry about the frequency f. So, for the prototype I already know that the some kind of rotation rate. So, I will denote it by omega for the prototype, that is given as 500 RPM. So, f is related to omega, the angular frequency, okay. And this is again something that I need to get out of the system. Let us talk about the length scale L. The length scale for the prototype is told to me that it is a 1/9 scale model. So, the prototype would be this is given to me LP, and for the model it is actually LP by 9. Okay. I can talk about the head, the pressure head for example. This was for the prototype, it is given as 250 meter, and for the model this is 10 meter. Rho is the density for the prototype, which is rho water, okay, 10 to the third kilogram per meter cube, and the same fluid is being used for the model, so that is also rho water. So, I am not writing the numerical value because we do not need it, okay, but if you want to write a numerical value, you are free to do that. In the end, it should not matter. Great. So, now let us get on by matching the Euler number and the Strouhal number. So, first the Euler number for the model should be same as Euler number for prototype for the dynamic similarity, and this would imply that the rho of model times u model square by p of model is rho of prototype u of prototype square by p of prototype. And from this I can infer that u prototype by u model is, so these would cancel out because I am using the same fluid. So, this would turn out to be Pp by Pm, those are the pressures, and then a square root. Okay. And we already know this is 250 meter, this is 10 meter, square root of that. So, I get a number 5. So, the velocity for the prototype is actually 5 times that of the model. Great. Now, let us work out what does the similarity with respect to the Strouhal number gives us, and this would imply that if I look at omega, so I could replace this f with the angular speed on both sides for the model and prototype. So, omega for the model times the length scale for the model divided by the u for the model should be equal to omega for the prototype, length for the prototype, and u for the prototype. I already know the scaling between um and up. Okay. I already know the scaling between the length scales. So, from this I can infer what is the scaling for the model, and that would turn out to be um by up times Lp by Lm times omega p. And if I plug these in, then this is 1/5 u model to u prototype, this is a 9th scale, and this is omega p, which is actually equal to 500 rpm. So, if you do the arithmetic, this turns out to 9 by 5 times 500, so 900 rpm. Okay. So, you must spin the pump, the model pump, at 900 rpm so that you get dynamic similarity. Okay. So, we have already ensured geometric similarity, and by ensuring the model speed or the speed of water through the model and the spin rate of the pump, the model pump, now the dynamic similarity is ensured. So, what would be the flow rate? So, the flow rate, as you know, the Q for the prototype would be the area, the cross sectional area of the pump times the average flow speed through it. Okay. So, I could write this as, let us say, pi dp square by 4 times the speed through it, which is up. And similarly, Q model would be pi d model square by 4 times model. I already know what is the flow rate through my prototype. Okay, that's 5 meter cube per second, and I need to estimate what is Qm. So, I could look at what is Qp by Qm, and that you can see is simply dP by dm whole squared times up by um. So, if you work these out, the dp by dm is 1/9, it is the 9th scale model, and up by um is here 5, and therefore, so this is so this would imply that my Q model would be simply okay, I have made a mistake here, sorry. The prototype is, so this is actually 9, and up by um is of course 5, all right. So, Q model is Q prototype divided by this quantity 9 square times 5, and you can work it out. This would be about 5 by 405 meter cube per second, which is 0.0123 meter cube per second. Okay. Let us now look at a problem where the modeling was going to be a little bit more complicated. Okay. So far I have given you examples where you apply the rules of dynamic similarity and everything works out. I now wish to give you an example from real life. In fact, I have encountered it myself during my experiments at the National Wind Tunnel facility, where you are unable to do dynamic similarity. Okay, and then how do you model in those situations?